Hi, everybody. This is qKleene. It's verification of quantum RAM made easy. This is a joint paper with Giulia De Santis and Margherita Zozzi and myself. So I'm here trying to show you the idea of qKleene. qKleene is not really anything new. It's just trying to put together regular expressions and quantum computation in such a way that the semantics and the collecting semantics becomes very clean and simple to define. So why do we need qKleene? Well, the first question is, what is program analysis? Typically, program analysis is an automated method in order to extract invariants or properties from code. So on the left-hand side, you have two loops nested, and you want to extract the meaning of those two loops. That program is quite tricky. I mean, you take some time to understand what's going on there. Program analysis is just an algorithm that tries to extract from that program all the red assertions that you can find on the right. They explain precisely what's happening at each program point during program execution. So take, for instance, the McCarthy function 91. That's a very tricky double recursive function, which is very hard to analyze statically and what I would say algorithmically. Well, there are program analysis like abstract interpretations and other methods that allows you to extract precisely the semantics of that function. If you look on the right-hand side of the slide, you can see precisely that the analyzer is able to catch that B will be bigger or equal to 91. And this no matter how you write the code. I mean, the code doesn't show the variable B to be assigned with the number 91. There's no 91 written anywhere in the code, but the analysis is able to extract that. So in order to fully understand the structure of an algorithm and the dynamic of an algorithm that tries to extract the semantics of a program, we need to specify the semantics of the program in such a way that the property of the execution are part of our semantic domain. So the execution is not anymore the execution of one single trace. You have an input and then you compute the next value up to the end, but rather is a set of possible values that hold at a given program point. Why do we need this? Well, we need this because if the domain of properties we want to deal with, like being 91 or being bigger than 91, which is an interval, an open interval, or being between 0 and 10, and so on, you can imagine that the real computation, the properties of real computation are all those pictures and images, which are basically geometric shapes, on the left-hand side. And that's the concrete execution. So at some point, you can imagine that at some point, the execution has some shape. Then you decide that you want to abstract those shapes into one possible shape, which is a square or a circle or a triangle. We choose the circle as an approximation. So we look for the smallest circle that includes the shape we are really computing, which is the one on the left. And then that is the abstract domain. The abstract domain in abstract interpretation is nothing else than a representation within a specific language, constrained language, of the property we want to express, and we are able to express from our concrete domain. In that case, just circles that include all the possible shapes like the star, the rectangle, the ellipsoid, and so on. That approximation so the abstract domain is the domain of approximated object, requires a concrete semantics that is able to express the object of our analysis, which are all those shapes on the left-hand side. So take these two programs. So whenever you compute in the concrete, for instance, we want to look at the invariant of the while loop, but then you run that and you see the computation. The computation produces the same invariant, but look what's happened. If we look what's happening with respect to the final assertion being x equals 0, the two programs are semantically equivalent. But if we consider the shape, the approximated shape, not being the set of values that are computed, but the interval of those values, you immediately observe that by looking at the interval, you lose information. For instance, the first loop correctly provides that x is 0, but the second loop correctly says that it can be 0 or 1. This is a loss of information that is very well known in abstract interpretation. It's called completeness and incompleteness. In the first case, we have a complete computation. In the second case, we have an incomplete one. Incompleteness is the error introduced in the analysis that requires a semantics which is specified in that way. Namely, is specified by assertions. Look what happened with these two different loops. We are still computing not in the quantum, but in the classical term. So in this case, you run the two computations, you got two intervals, and now, although the two programs are semantically different, they are looked equal because incompleteness in both cases produces spurious outputs that lead the two constraints being the same interval, 0, 1 or 0, 1. Okay, so what is qKleene in all this story? qKleene in all this story is a language which includes expressions which are made by classical expression and quantum expressions that allows to provide regular commands of these expressions. That means concatenation, that means the disjunction, and that means the iteration. And this is why it's called qKleene. So what is a program in qKleene? A program in qKleene is nothing else than a regular expression of these commands. So we have unbounded classical registers and bounded quantum registers that will respectively denote integer numbers and bounded quantum information. So a qKleene program is nothing else than an object within the set of all possible qKleene for n variables which are classical, m variable which are quantum, and each quantum variable is just a register of k elements. So the regular expression, the standard expressions, what we call it in the little paper, the core qKleene, is a set of expressions that is somehow minimal. We have classical expressions with n variables, which can be the assignment of an arithmetic expression to a classical variable, or the assignment of an expression to a quantum variable. Then we have the arithmetic expressions that are addition, subtraction, because we are dealing with integer numbers, or itself a variable. We have Boolean expressions like the standard ones in a program, and in particular we have these me's, which is partial measure of a quantum register. So basically the memory is split in classical unbound classical variables, which is unbounded registers, and bounded by k quantum variables, which is a register of k quantum bits. The idea of measure is that we can measure part of that register, namely, for instance, just measuring the first three elements of the variable that we are considering. This is the structure of the basic expressions. So in order to store information in qKleene, we have the store. The store is nothing else than a pair that acts in a domain which is a pair of objects, which are tuples of integers that correspond to the number of variables we have on the classical side, and tuples of q states, which are what we can build as a register of k quantum bits. Basically, an assignment is nothing else than assigning those elements to the corresponding domain. So whenever we have a qKleene expression R, then we have the store is split in two parts, the classical store and the quantum store. And they are corresponding to assignment into the registers of unbounded classical variables for the classical variables and or the quantum registers that are bounded by K. The semantics of the qKleene is made inductively. So whenever we are able to give the semantics of the basic expressions in the core, then that provides the semantics of the elements, the basic elements in the induction. Then we can build expressions like in control flow graphs. Therefore, in the end, the computation in our qKleene program are nothing else than computation over a control flow graph that are expressed by regular expressions of these elementary core qKleene expressions. So we have concatenation, disjunction, and iteration. And the semantics of them is specified in a standard way, namely, concatenation is nothing else than composition of functions. Disjunction is nothing else than the union of elements, and iteration is nothing else than the union of all the possible prefix of, namely iteratives, partial iterations, until we complete omega. So the semantics is given in this way. You can split the semantics in two parts, the classical and the quantum semantics, and you will see that the classical part is precisely the standard semantics of programming language, like those of regular expressions. And together with that, we have many other elements such that, for instance, we have the skip, which is do nothing, the question about B, a Boolean guard, which means we just collect those and make the Boolean guard, those states that we are talking about classical state that make the Boolean guard true, and the assignment that simply act on the classical side by replacing the variable with the new value computed. What makes the classical part different is the partial measure, and in this case we choose that once we measure the quantum state, we can either have a computation that is probabilistic, so we choose the output and we keep going classically with the given probability, or we simply pick up the most probable output and we continue with that. The computation for the quantum side is precisely the standard one, where we have unary operation, invertible operations, that is U in the picture. The nice thing of this qKleene is that we can simply inherit the standard semantics of Hoare proof system. So this is completely standard. We have nothing to do with that. That's simply inherit and copy paste from Hoare paper, and we got the definition of a Hoare logic that perfectly fits inside our framework. What we need to do is to give the semantics, so to provide exactly the meaning of the basic expressions in our core qKleene program. And this is an example. Consider, for instance, this little program. It has an iteration that is contained inside the square, which is the red one, and that is iterated many times until we reach 3, and then we exit. We call this program qFlip. So we want to prove the Hoare triple that is below. Namely, no matter how we start for any x in z, and q is in a qubit, so we have any possible input at the beginning of this program, then we come out at the end where x is 4 and q is an entangled state. So we just need basically that rule, because the other rules for concatenation are pretty straightforward. In that rule, we need to express that invariant. With that invariant, that simply says that whenever we iterate an even number of times, then we can have that q can be either 0 or 1. But whenever we have an odd number of times of the iterates, then we have an entangled state. That's exactly the meaning of the invariant. And for that invariant, we are able to specify precisely and to prove the Hoare triple to be true. So why all this? Well, qKleene has a very simple structure of regular comments, and this encodes control flow graphs. Control flow graphs are the basic for making program analysis. So we would claim that qKleene makes program analysis easier. The second thing is that we have a very simple Hoare logic-like structure which is completely inherited from Hoare logic. We just need to fix the semantics of the basic core expressions, in particular for those that involve quantum computations. The third point is that this semantics is a collecting semantics in the standard Clouseau and Clouseau framework. Therefore, it's pretty ready for abstract interpretation. On this, we can build an abstract interpreter that exploits that structure by, for instance, approximating classical and quantum states into approximated abstract states. Thank you very much.